This video is demonstrating the layout and simulation of an 8-bit divider. And so here we have the divisor A and the dividend B. They're both 8-bit numbers, and then at the bottom we have the quotient down here and the remainder over here. And so the way this circuit works, the way the circuit works is it takes and compares, it uses the shifting and subtracting method of division, which is the same, kind of the same thing as long division with decimal, where you compare the divisor to the first number in the dividend, and if it's greater, then you do nothing and you go to the next one, or then you check the next two numbers, and if the divisor is less than or equal to the first number in the dividend, you find the number of times that the divisor goes into the dividend, so that is that part of the quotient, and then multiply the number of times the divisor goes into the dividend by the divisor, and then subtract that from that section of the dividend. In binary, it's a lot simpler than that. You just check if you start off by checking if the first bit of the dividend is greater than, less than, or equal to the divisor, the whole divisor, that is. And if it's greater than or equal to, if the dividend is greater than or equal to the divisor, then you subtract. And the divisor is either going to, or the divisor is either going to go in the dividend 1 time or 0 time, as a result of the binary format. So you don't have to do any, don't have to worry about any multiplication. So if the dividend is less than the divisor, then you subtract nothing and you go to the next, you bring in the next bit and you compare the dividend with the next 2 bits, the first 2 bits rather, of the divisor, dividend, excuse me. And so the way I've chosen to implement that is you have this first block here is a binary comparator, and there are binary comparators that exist in the 7400 library, but I couldn't get them working the way I needed. Instead of one output being high and then the other 2 outputs being low, one output was high and then the other 2 outputs were showing X's, or indeterminate outputs, I believe is what that represents. And so I had to go in and create a comparator, an 8-bit comparator from logic gates. And so this is the most significant bit comparison, and if A is greater than B, that means A is 1 and B is 0. And so this AND will have both inputs high, this AND will have both inputs 0, and this NOR gate will have 1 high and 1 low input. So the output of the NOR gate, which would be the A equals B term, is going to be 0. The output of this top AND gate, which is the B is greater than A term, is going to be 0. And the output of this bottom AND gate, which is A is greater than B, will be high. And so the same thing happens for this AND gate when B is greater than A. This input is 1 because that means B is 1, and A is 0, and so the 0 is inverted and it becomes 1, and this output is high. And again, the output of this NOR gate is going to be 0 because it's going to have, it's going to have 2 terms, or 2 different terms rather, on its inputs. And then when A is equal to B, that means either A is 0 and B is 0, or A is 1 and B is 0. So both AND gates will have different inputs, which means the outputs of both of those will be 0, and the inputs of both inputs of this NOR gate are going to be the same. So the output of the NOR gate is going to be high. And so if one of the two AND gates, if that output is high, then we know, since this is the most significant bit, we know that either A is greater than B, because the most significant bit of A is greater than the most significant bit of B, or B is greater than A, because the most significant bit of B is greater than the most significant bit of A. And so these are sent to cascaded OR gates. They would be 8 input OR gates if you were to just draw the schematic. Or if you were using one of the digital libraries that has like larger number of input OR gates, but they don't have the actual like. Oops. Sorry about that. But they don't have the numbers. And so for the equal terms, you have to check each term to determine if all of A is equal to all of B. And so the outputs of each of the NOR gates, which are the A equals B term, are all sent to an 8 input AND gate, which is represented by cascaded AND gates here. And then that's just sent to one of the outputs. And so to prevent a false positive on the greater than or less than term, each succeeding bit, the greater than or less than terms are ANDed with the previous bit's equal to term. Because if A is equal to B, then this AND gate will be low and this AND gate will be low. And so there's going to be no output to the OR gates. And then coming to the next bit, if A is greater than B, if the second most significant bit of A is greater than the second most significant bit of B, and the most significant bit of A is equal to the most significant bit of B, then this AND gate will be high, or this AND gate will be high. The bottom AND gate will be high, excuse me. If the opposite is true, the top AND gate will be high. And so it keeps on going. And it's just ANDed with all the previous terms. So like the A4 term here, if A is greater than B, these bits, the fourth least significant bits, are if the fourth least significant bit of A is greater than the fourth least significant bit of B, then this bottom AND gate will be high, and it will be ANDed with the equal terms from the previous three bits. And so that's effectively saying that if the fourth least significant bit of A is greater than the fourth least significant bit of B, and the previous bits of A and B are equal, then you'll have a positive output here, or a high output here. Now, this next block here is much more simple. It's just 2 gates, a NOR and a NAND. This just converts the 3 outputs from the 3 outputs from the comparator to 1 output, and that's used as a selector for this multiplexer and for the controlled add-subtract here, as well as being the quotient for this particular bit. Because when the way the selector is set up, the A equals to and A is greater than B terms are both NORed, and the output of that is NANDed with the A is less than B term. And so what happens is, if A is equal to B, or if A is greater than B, then the 2 inputs of the NOR gate be different, and so the output of the NOR gate will be low. And then the output from the A is less than B term will be low, and so you have two low inputs on a NAND gate, and so you're going to have a high output from the NAND gate. If the inverse is true, if A is less than B, then the two inputs, the A equals to B and A is greater than B, are going to be 0, and so the two inputs on the NOR gate are going to be 0, which means the NOR gate output will be high, and so the NAND gate will have two high inputs, which means it will have the output will be low. And so as far as the quotient is concerned, that's effectively saying that if A is less than B, that means that the divisor is greater than the dividend and will not go into the dividend at all. And so you would put a 0. If you were doing this out in long division, you would put a 0 above the bar for that bit. If the opposite is true, if A is equal to B or A is greater than B, that means the divisor is equal to or less than the dividend, which means that it goes into the divisor goes into the dividend one time. And so you would, if you were doing it out in long division, you would put a 1 above the bar. As far as the rest of the circuit is concerned, it's used as a selector. So for this multiplexer, it is, stepping into it, it is an 8-bit 2-to-1 multiplexer. And so one of the inputs of the multiplexer is held low, and the other input is 1 bit of the divisor. And so when the selector is low, that means that the divisor is greater than the dividend, and we want to subtract a 0 from the dividend. And so the selector would be low, the output of this inverter would be high, and so this AND gate is going. This AND gate will have a low input, and so the output is just going to be low regardless of what the data is. And this AND gate will have one input set to high, so it's going to act as a buffer. And since we have the other input set to low, the output of this AND gate is going to be low. And so both of those terms are then ORed just so we have one output. And then the output of the multiplexer is sent to the B term of controlled adder-subtractor, while the most significant bit, the A7 bit, is sent to the A0 term of the A7 bit of the dividend is sent to the A0 bit of the controlled adder-subtractor, while the other bits are padded to 0. And I forgot to mention the same thing's happening with the binary comparator. We're taking the A7 bit of the dividend and comparing that to the whole divisor, and for the binary comparator and the controlled adder-subtractor to work properly, the rest of the bits have to be padded to 0 so that we know what the input's going to be. So it's not just some random garbage term. And so then this controlled adder-subtractor is just made out of a couple 7483s in series with each other, or cascaded, I guess would be a better term. And the way this works is the C-in term is connected to one input on an XOR gate, while the B term is connected to the other input. The output of this is sent to the B input on the controlled adder-subtractor, while the A input is just sent straight to the A input of the controlled adder-subtractor. What this does is, if the C-in term is low, meaning the divisor is greater than the dividend, the divisor is, if the C-in is low, that means that the divisor is greater than or equal to the dividend. No, I'm sorry, I'm getting it backwards. The dividend is greater than or equal to the divisor. And so we're subtracting the divisor from the dividend. And when you set one input of an XOR gate low, then it acts as an inverter. And so if the B input here is 1, 1 XOR with 0 will be 0. And if the B input is 0, shoot, I have that backwards, I believe. So basically how this works, to simplify it a little bit more so it's not confusing, because apparently I'm confusing myself, is depending on the selector input, the XOR gates will either pass B or will find the 2's complement of, or the inverse of B. And so when the C in term is high, yeah, I had the function of the XOR gate backwards, I'm sorry about that. When C input term is high, the XOR gates will act as an inverter and will invert the B term. And the way to find the 2's complement of a binary number is to invert it and add 1. And so the XOR gates perform the inversion, and then the carry in is added to that. Because the way the adder 7483 works is it adds the A term to the B term and then adds the C in term. And so if C in is 0, it doesn't add anything. If C in is 1, it'll add 1 to it. And it's just there mostly so that you can cascade them like this. But it is very helpful for creating a controlled adder-subtractor. And so when the C in term is 0, the XOR gates just act as buffers and will pass the B1 or the B in terms. And so that is 1 bit of the divider. That will find 1 bit of the quotient right here. And so the shifting method, or the shifting part of this method, comes in when you cascade to the next bit. You take the 6 least significant bits of the sum of the controlled adder-subtractor and send those to the 6 most significant bits of the next controlled adder-subtractor and the next binary comparator. And then the A6 term, the next most significant bit, next least significant bit, is set to the least significant bit of the next binary comparator and the next controlled adder-subtractor. So that would be this right here goes to the A0 term, and then of the binary comparator, and then goes to the A0 term of the controlled adder-subtractor. And then the same thing happens again. You take the 6 least significant bits of the current controlled adder-subtractor and set them as the 6 most significant bits of the next controlled adder-subtractor and the next binary comparator. And then again, you take the selector as the next bit of the quotient, and it keeps on cascading like that until you get to the last bit, and the output of the full output, the whole sum of the controlled adder-subtractor will be set as the remainder, and then all of the selectors are sent to a bus and taken as the quotient. And so the output, I'll pull up in a second. There we go. That's the output window. I got to run it real quick. I chose 3 values for the divisor to demonstrate the apparently chose poor values. Give me a minute. Alright. That is weird. That's bad. Alright, my apologies on that. Okay, so I chose one value for the divisor that was greater than the dividend, one value for the divisor that was equal to the dividend, and then one value of the divisor that was less than dividend. And so all of these values are in decimal. And so A was chosen to, the dividend was chosen to be 8. And the first value of the divisor was chosen to be 67, which, as you can see here, goes into 8 as 0 times, and the output, the remainder is therefore 8. When the divisor and the dividend are equal, the quotient is 1 and the remainder is 0 because 8 goes into 8 exactly 1 time. And then when the divisor is less than the dividend, in this case 3, 3 goes into 8 2 times with a remainder of 2. And so that is everything. So you make an 8-bit divider in PiecePlace, using PiecePlace.